Welcome to today's deep dive. So I want you to imagine for a second that you are, sitting at your computer and you're just staring at a countdown clock.
Oh, we've all been there.
Right. You are furiously refreshing a web page because you want to buy a highly anticipated item. Maybe it's front row concert tickets or a limited edition sneaker drop or like the absolute latest gaming console.
And you're just praying your internet holds up.
Exactly. And you, along with millions of other people around the world, are all hammering this exact same website at the exact same millisecond.
Yeah.
And yet, somehow, the site doesn't crash. You actually get through. The page loads, your cart updates, and the order processes. Have you ever stopped to wonder what invisible architecture actually keeps the internet from just completely buckling under that kind of massive instantaneous pressure?
We take that stability completely for granted, I think. But intuitively, a system that's receiving millions of simultaneous requests should just collapse under its own weight.
Oh, 100%.
The fact that it doesn't is the result of some incredibly clever architectural orchestration happening behind the scenes, specifically in how we manage data retrieval.
And that invisible orchestration, that is our mission for today. We're unpacking an article by software engineer Aaron Rose. It's titled The Secret Life of AWS, the Memory Layer, which focuses on Amazon ElastiCache. And to help us really understand the mechanics of this, the author introduces us to two illustrative characters. We've got Margaret, who is a seasoned senior software engineer, and Timothy, who's her junior colleague.
Right.
And we find them working in what the author describes as this metaphorical Grand Victorian library in London. It really sets this tone where, code quality is the unspoken objective and craftsmanship is absolutely everything.
Setting the scene in that deliberate, careful environment, it highlights this really stark contrast with the absolute chaos that is currently unfolding on Timothy's monitor.
Right, because things are going wrong.
Exactly. A marketing flash sale has just gone live, and it's driving an unprecedented surge of legitimate traffic to their storefront.
And legitimate is the key word there. It's not a cyber attack.
No, these are real customers, and the application is technically surviving. I mean, they aren't dropping customer orders, but Timothy is staring at his AWS Cost Explorer, and the daily bill is just exploding.
Wow.
This is, it's the classic double-edged sword of cloud computing.
Yeah.
Your system scales to meet demand, but you pay for every single ounce of that scale.
Yeah. So Timothy starts digging into the logs, and he discovers that his DynamoDB read capacity costs for their product catalog are just going through the roof.
Yeah.
A single top-selling item, in this case, it's a mechanical keyboard, has been read from the database 400,000 times in one single day.
Which is a massive amount of reads.
It's huge. And here's the real kicker of the situation. Margaret walks over, she looks at the dashboard, and she asks him if the price or the description of that keyboard has changed at all during those 400,000 requests. And Timothy has to admit that it hasn't. It has been exactly the same all week. They are literally paying Amazon Web Services a premium to tell them the exact same piece of unchanging information almost 500,000 times.
What's fascinating here is the underlying mechanical reality of why those repetitive queries are so punishing.
Okay.
Primary databases like DynamoDB, or even, relational options like Amazon RDS, they are fundamentally built for durability. They are the system of record.
Right, the single source of truth.
Exactly. Their primary uncompromising job is to ensure your data is never lost, regardless of power failures or server crashes or anything else.
Okay, that makes sense.
And to achieve that ACID compliance and durability, they must physically write data to and read data from storage disks. And reading from physical storage, even modern storage, is a computationally expensive operation.
Because it's a physical action.
Right. It consumes processing power, it takes time, and in a cloud environment, it consumes provision throughput, which ultimately costs money.
Okay, let's unpack this because I want to make sure we are really visualizing the sheer inefficiency of what Timothy's application is doing here.
Yeah, go for it.
It's like, imagine working at a help desk, right? And every time someone asks you the price of this mechanical keyboard, you have to stand up, walk down 3 flights of stairs to a secure basement filing cabinet.
Sounds exhausting.
Right. Unlock it, pull out a heavy fireproof folder, read the price, walk all the way back upstairs and tell the customer. And you do this 400,000 times in a single day.
Wow.
Instead of just, writing the price on a sticky note and slapping it right there on your desk.
That is, honestly, the basement filing cabinet is the perfect way to visualize a primary database.
Okay.
It is incredibly secure. If the building loses power, your records are completely safe down in the basement.
Right, they aren't going anywhere.
But going down those stairs for quick, repetitive questions is just a terrible misuse of resources.
Yeah.
When you ask a heavy, durable machine to perform physical disk reads thousands of times a second for static data, you just exhaust its throughput capacity.
Oh, wait, let me push back on this for a second.
Sure.
Isn't a database supposed to give you the data when you ask for it? Like, why are we punishing the database for doing exactly what it was engineered to do? If I ask DynamoDB a question, it's just fulfilling its fundamental purpose by giving me the answer.
I mean, in theory, yes. But in software architecture, especially at enterprise scale, relying on a single tool for every phase of a request lifecycle is an anti-pattern.
Oh, okay.
A primary database is built for truth and permanence, not velocity. Margaret points out to Timothy that for read-heavy, unchanging data, you do not want to constantly interrogate the system of record.
Because it's too expensive.
Too expensive and too slow. You need to introduce a high-speed middleman to intercept those repetitive queries.
Gotcha. So to build that sticky note for the desk, Margaret actually heads to the whiteboard. Sending the application to the basement filing cabinet is financially unsustainable, so she introduces this high-speed memory layer, which is Amazon ElastiCache.
Right.
And she specifically chooses the Redis engine over something simpler, like Memcached.
Yeah, and that's an important distinction. Memcache definitely has its place for very simple, flat key value caching. But Margaret's choice of Redis, it really aligns with modern enterprise standards.
Because it can do more.
Exactly. Redis supports highly advanced data structures, so things like lists, sets, sorted sets, and that gives developers so much more flexibility. Crucially, Margaret provisions this as a Redis cluster, utilizing what's called cluster mode with replication.
Which is a vital safety net, right? Because if you have an application that is serving millions of requests and you're routing all of them through this cache, that cache absolutely cannot become a single point of failure.
Oh, absolutely not.
Like if your cache node goes offline and you don't have replicas ready to take over, all of that massive flash sale traffic is instantly going to slam right back into DynamoDB.
And the whole system crashes anyway.
Exactly.
Yeah, that failover capability is totally non-negotiable at scale. In cluster mode, if the primary node handling request experiences a hardware failure, a replica node is automatically promoted to primary.
So it just fixes itself.
Right? Maintaining high availability without human intervention. The application barely registers a blip, and the database remains protected.
And this isn't just some, clever software routing trick. This really comes down to physical hardware limitations. We are talking about the difference between solid-state drives and actual RAM. Primary databases store their truth on SSDs. They are fast, sure, but they're still non-volatile physical disks. ElastiCache, on the other hand, operates entirely in RAM, random access memory.
Yeah.
Because there is no physical disk I/O, retrieving data from RAM takes, like, less than a millisecond.
The velocity difference is just exponential.
Yeah.
But that speed introduces a critical architectural trade-off.
Okay, what is it?
RAM is volatile memory. If the ElastiCache server loses power or the container crashes, everything stored in that memory is instantly and permanently wiped out.
Poof, gone.
Gone. Solid-state drives are non-volatile. You could unplug a database SSD, plug it back in 5 years later, and the records are totally intact.
Oh, wow. So if retrieving data from RAM is less than a millisecond and it's exponentially faster than a solid-state drive, why don't we just build the entire database in RAM and skip the physical disk completely?
Well, that's exactly why, because of that volatility. You can't put your primary system of record in something that gets wiped the second the power flickers.
Right. So you rely on the basement filing cabinet so the company doesn't lose its historical records if a localized power grid goes down, but you use the RAM on your desk as a temporary workspace for pure speed.
Precisely. You decouple durability from velocity, you let DynamoDB handle the permanent truth, and you let ElastiCache handle the blistering speed.
I love that. Okay, so Margaret and Timothy have provisioned this lightning-fast Redis cluster, but spinning up the infrastructure is only really half the battle.
Oh, yeah.
The application itself needs a strict set of rules. It needs to know how to navigate between the sticky note and the basement. And Margaret implements this by updating Timothy's Node.js application to use the cache aside pattern.
Yeah, the cache aside pattern. It is an incredibly elegant approach because it dictates that the application code, not the database, is the traffic cop.
Okay.
The cache doesn't magically intercept traffic on its own. The application actively orchestrates the flow.
How does that work?
So when that very first customer of the day requests the mechanical keyboard, the application's first program step is to query the ElastiCache Redis cluster.
But since it's the very first request of the day, that sticky note is completely blank. The cache is totally empty.
Exactly. The application looks for the keyboard data in RAM, it fails to find it, and it triggers what engineers call a cache miss.
A cache miss, okay.
Right. And the application logic dictates that upon a miss, it must fall back to the system of record. So it queries DynamoDB, retrieves the heavy data from the physical SSD, and serves it back to the user.
But it doesn't just stop there.
No. Before closing out the request, the application performs one final crucial step. It saves a copy of that keyboard data directly into ElastiCache.
Here's where it gets really interesting, because now the trap is set. Half a second later, customer number 2 asks for the exact same mechanical keyboard. The application checks the Redis cache first, just like before, but this time, the data is sitting right there in RAM.
And that is a cache hit.
Yeah.
The application grabs the data in under a millisecond, returns it to the user instantly, and bypasses DynamoDB entirely.
Wow.
And for the subsequent 399,099 customers who want that keyboard, the application serves them directly from memory.
That's amazing.
Yeah, the DynamoDB read metrics drop to absolute 0, and the AWS bill immediately stabilizes.
It's like a bouncer at an exclusive club holding a VIP list.
Okay, I like this.
If you walk up to the door and you aren't on the list that's a cache miss, the bouncer has to radio the manager in the back office, verify your identity, wait for approval, and then write your name down on the clipboard. It creates a massive bottleneck at the door.
Right.
But if your name is already on the list to cache hit, you just walk right in without the manager ever even being bothered.
That's spot on. And following that logic, Margaret implements a technique called cache warming.
Cache warming.
Yeah. Because think about it. Even that very first customer who triggers the cache miss experiences a slight delay, right? Because the application checks the cache, fails, and then routes to the database.
Right, there's a tiny penalty there.
Exactly. But if you already know what your highly requested items are going to be like, say, the mechanical keyboard that's headlining a flash sale, engineers can proactively preload those items into ElastiCache during the deployment phase.
Oh, so you literally hand the bouncer a pre-written VIP list before the doors even open for the night.
Yes.
So when the clock strikes midnight and the sale starts, even the very first customer is a cache hit.
It guarantees maximum efficiency from second one. The database is completely shielded from the initial traffic spike because the memory layer is already primed with the answers.
I mean, it sounds like an absolute silver bullet. Database reads are flat, the application is returning data in sub-milliseconds, and Timothy's AWS bill is completely cured.
It sounds perfect.
It does, but Timothy realizes that while the caching system works flawlessly for performance, it actually introduces a dangerous new problem regarding reality. What happens when the facts change in the real world? Like if the marketing team decides to slash the price of that keyboard halfway through the flash sale, they are going to update the price in DynamoDB.
But as we just established, the application is no longer checking DynamoDB.
Right.
It is exclusively reading from the Redis cache.
So if the old price stays permanently written on that sticky note, the customers are going to see completely wrong data. They'll be buying the keyboard at the old higher price while the database says it should be cheaper.
It was a huge problem.
Massive. And Margaret addresses this by quoting a famous computer science adage. She says, there are only 2 hard things in programming, naming things and cache invalidation.
Oh, that quote is legendary. Cache invalidation is notoriously difficult to manage at scale. It's essentially the process of declaring that the lightning-fast data currently sitting in RAM is stale and forcing the system to go retrieve the fresh truth from the database.
So how does she fix it?
Well, Margaret's solution for this application is implementing a TTL, which stands for a time to live.
Okay.
She uses a specific Redis command called setx to instruct the cache to automatically self-delete the keyboard data after exactly 1 hour.
This raises an important question, though, about the fundamental philosophy of caching architectures. Implementing a cache forces a conscious compromise around data consistency, doesn't it?
It really does. You are actively choosing to trade a defined amount of data staleness in exchange for blazing fast scalability.
Right.
By setting a TTL of 1 hour, Margaret is accepting that for up to 59 minutes and 59 seconds, a customer might potentially view outdated information. But the moment that hour expires, the item is purged from RAM. So the very next customer request triggers a cache miss, forcing the application to fetch the freshly updated price from DynamoDB, which is then cached for the next hour.
I have to play devil's advocate here, though, and kind of push back on Margaret's solution.
Go ahead.
An hour feels like an absolute lifetime in modern e-commerce. If the price drops dynamically, or worse, if an item sells out in 5 minutes, an hour of staleness means you could have thousands of angry customers who overpaid, or you've just sold ghost inventory that doesn't actually exist in the warehouse.
Yeah, that would be bad.
So how do engineers actually decide how long that TTL timer should be without causing just utter chaos on the back end?
It is the ultimate balancing act, and it requires categorizing your data based on its volatility.
Okay, what do you mean by that?
So for a blog post or a news article, a TTL of 24 hours might be perfectly acceptable because the text rarely changes.
Right, the words are the words.
Yeah, exactly.
Ah.
But you're absolutely right. Applying a blanket 1-hour TTL across an entire e-commerce catalog is a recipe for disaster. Experienced engineers utilize a blended caching strategy.
A blended strategy.
Yeah. So the product description and the high-resolution images, those might have a TTL of a week. The price might have a TTL of 3 minutes.
Oh, wow.
And the actual inventory count, like the literal number of keyboards left on the warehouse shelf that might bypass the cache entirely.
Wait, really? Just not cache it at all?
Right. The application might be programmed to always read inventory directly from the primary database because that specific metric must be perfectly, consistently accurate at all times.
That makes total sense. So you aren't forcing the entire application to abide by a single caching rule. You cache the heavy, static assets for as long as possible, and you query the dynamic, highly critical data in real time.
Exactly. It allows you to protect the database from the bulk of the query weight while still maintaining integrity where it matters most.
Okay, so Timothy and Margaret, they had this blazing fast Redis cluster. They have their cache-aside pattern routing the traffic, and they have finely tuned TTLs keeping the data relatively fresh. But the deep dive leaves us with one highly specific hidden trap. And this trap exists specifically when you are building this memory layer inside modern serverless environments, like AWS Lambda.
Yeah, this is a critical operational warning in the article. Implementing caching in a serverless architecture introduces a technical gotcha that can silently take down your entire infrastructure if you don't understand the underlying execution environment.
And the warning explicitly centers around connection management in serverless. It states that when engineers connect to ElastiCache from inside an AWS Lambda function, they absolutely must initialize the Redis client outside the main handler function.
Yeah, and to understand why this is so catastrophic if done wrong, we need to look at how AWS Lambda fundamentally operates.
Okay, let's hear it.
Lambda functions are ephemeral compute containers. When a request comes in, AWS spins up a tiny container, runs your code, and then eventually spins it down.
It just disappears.
Right. And establishing a TCP network connection from that container to the Redis cluster requires a multi-step handshake. It takes time, and it takes compute resources.
Okay.
If you place the code that initializes that TCP connection inside the main handler function, well, every single time a customer requests the keyboard, Lambda creates a brand new, unique network connection to ElastiCache.
Which means if you have 400,000 customers clicking on that keyboard, you are opening 400,000 separate simultaneous network connections.
Exactly. And if we connect this to the bigger picture of network architecture, Redis is phenomenally fast at retrieving data from RAM, but it has finite resources for managing open TCP sockets.
Oh, I see where this is going.
Yeah. If you barrage the cluster with thousands of new connection requests a second, you will rapidly exhaust its connection limit. The cache will freeze up, the connections will time out, and your application will crash.
So you've successfully solved your DynamoDB disk read bottleneck, only to accidentally engineer a massive failure at the TCP network layer.
That's exactly what happens. It's a classic case of just shifting the bottleneck.
Okay, so by moving that single line of code to initialize the Redis client outside the handler function, what does the execution environment actually do differently?
So when it sits outside the handler in the global scope of the function, AWS Lambda preserves that initialization. It performs the TCP handshake and creates the connection to Redis exactly once during the container's cold start phase.
Okay.
Then, as subsequent customer requests are routed into that exact same, now warm container, the execution environment reuses that single, already open TCP connection.
So what does this all mean? It's like keeping the phone line permanently open with the Redis dispatcher.
Yes.
Instead of picking up the phone, getting a dial tone, dialing their 10-digit number, and saying hello from scratch every single time a customer places an order, you just leave the phone off the hook. When a new order comes in, you just shout it down the open line.
That is a brilliant way to conceptualize it. Establishing the line of communication is the expensive part. Once you have the dispatcher on the line, you keep him on the line.
Wow.
One simple scoping change in the code transforms an application from a connection-exhausting menace into a highly efficient, reused resource.
It really circles back to that grand Victorian library craftsmanship we talked about at the very beginning. Like, when you are operating in the cloud at massive scale, the microscopic details, like exactly where a single variable is initialized, they really, really matter.
Oh, they do. They're literally the difference between an application surviving a flash sale and completely crumbling under the pressure.
Let's zoom out and just summarize the architectural journey we just went on.
Sure.
Timothy and Margaret started with a system that was financially struggling and incredibly inefficient because it relied purely on durable physical disk storage to answer every single repetitive question. And by introducing Amazon ElastiCache and Redis and carefully orchestrating the cache-aside pattern, they fundamentally transformed how their application handles scale.
They traded a system that was punishing a physical disk 400,000 times for a static answer, and they replaced it with a hyper-efficient sub-millisecond memory layer. And by accepting a manageable amount of data staleness through TTLs, they achieved massive gains in both performance and cost reduction.
And for you listening, this invisible dance between permanent storage and temporary memory, it's happening around you every single time you pick up your phone.
Every single time.
Like, why does your social media feed load the second you open the app? Why does your streaming service populate movie artwork without buffering? Because underneath almost every seamless digital experience, there is a memory layer, like ElastiCache, intercepting your requests, answering them from RAM, and protecting the heavy databases hidden in the basement.
Caching really is the unsung physical mechanism that makes the modern expectation of instantaneous a reality.
It is. But I want to leave you with a final thought to kind of mull over. We've spent this entire deep dive exploring how caching reacts to what people have already requested, right? The first person takes the cache miss, so the next person gets the cache hit. But imagine a future where AI gets so sophisticated at tracking your personal behavioral habits that it can predict exactly what you're going to click on next.
Oh, wow.
What if the system automatically pre-warms a highly personalized cache just for you, milliseconds before your finger even touches the screen? Are we moving toward a web where nothing is ever truly loaded on demand anymore, but absolutely everything is waiting for us in memory before we even realize we want it?